Hello and welcome back to Calculus 2, section 8.5 on partial fraction decomposition. So this is another one of those painful calculations that we need to do to transform the integral into the form where we can integrate. Now, you might be asking, what is partial fraction decomposition? Well, it's this algebraic calculation that you do to turn a single rational expression into sum and difference of multiple rational expressions. So we are going to do the problem forwards, and then we're going to work on partial fraction decomposition and show that actually it gives us what we need. So let's say that you have 3 divided by x plus 2, and you are adding that to 5 divided by x minus, let's say, 3. And you are transporting yourself mentally back to elementary algebra, algebra 1, to add these two fractions by using basic common denominator. So now we are actually talking basic algebra 1. What do I need to do? I need to multiply the left side with x minus 3 and the right side with x plus 2, which creates the common denominator of x plus 2, x minus 3. And on top, I have 3x minus 9 plus 5x plus 10. And finally, I have a total over here of x plus 2, x minus 3, and we have 8x plus 1. So these are... So this is the calculation from elementary algebra. Done forward. Partial fraction decomposition is, this is where you start, and you need to give me this. Because, guys, I cannot integrate this. It's not U sub, it's not by parts, you can't do trig sub. You can just cry looking at this, right? That's it. That's the best you can do. However, if we can come up with some kind of method, what I call witchcraft, right? To decompose that into this, can you integrate each one of these independently? What kind of integral would this be? This 3 over x plus 2. What should I use to integrate if I just have that? Log, right? You use U sub to come up with the ln, right? So the reason why we do this partial fraction decomposition is to take something that is complicated all the way to the right and decompose it, right, into partial fractions, partial fraction decomposition. And when you get a whole bunch of these separately, you will be integrating each one independently from the other, and you will be getting logs and inverse tangents and all of these. So main players here are U sub, log, and inverse tangent. Those are your biggest players. Inverse sine might peek in too. So I just say hello. Yes?
Can you just split? So AX will be just 8x over the whole denominator equals 1 over the whole denominator and simplify?
You can, but you still don't have enough, because this will have a middle term of negative x, and you can't use U sub because you don't have minus 1. So, yeah. So, no, we are stuck with it. Trust me, mathematicians are the laziest people on the planet. The reason why we generalize things over here is just to do less work next time around. So trust me, we're not going to go through a 2-page calculation for no reason. All right, ready? Everyone is everyone warmed up? All right, lock the doors. Let's go. So let's see in which way we get to decompose. We get to decompose this expression. So my goal is to get the 3 over x plus 2, and so after I'm done, that's the answer. All right, so we are starting partial fraction decomposition problem. Nothing else in the world exists right now. This is it. You're looking at this and you want to decompose. So what do you say? You say, okay, these two guys over here are linear, both. So you are expecting to get the form of a over x plus 2 and b over x minus 3. How do I know this? We memorize 4 cases which are used as a setup. This is the first out of 4 cases that, so when we have a linear factor in denominator, you put a single constant up there, so single constant a. The other one is also linear, and you should put a, but a is already taken, so you put b. If you have 3 of them, you would add c. If you have 4 of them, there will be a d term, and so on. So this is scalable, right, to go up. So the number of linear terms, number of linear factors here is the number of terms that you get on the other side. In this case, we only have 2. So now we have this, and this over here is now the setup for your problem. So what is the only thing that I can do looking at this right-hand side? The only thing that I can do is to do the common denominator and just add these together. So we just go and multiply by x minus 3 and x plus 2. So now we have the common denominator of x plus 2, x minus 3. And we have ax minus 3a plus bx plus 2b. So these are, this is just algebra, right? And now we are comparing the original fraction with the new fraction. Do you see that they have the same denominator? So the tops, right, the numerators must be the same. So when I compare these two, I get the equation which says 8x plus 1 is equal to ax minus 3a plus bx plus 2b. I'm clearly looking for values of a and b, because when I get values of a and b, I get to plug them in, and then I will have the answer that I'm looking for, right? So now I have to solve this equation on the bottom. Now, before you scream, hey, 1 equation, 2 variables, we can do something that you will eventually learn in linear algebra if you take it. So whatever trick I'm going to use now, you will learn it in linear algebra. Pay attention. Do you see that on the left-hand side, I have a term that contains x, and I have terms that contain x on the right? I'm going to pool that together into a single equation, and then I have a term that it's a constant on the left and terms that are constants on the right. That's going to be my second equation. I'm creating a system of 2 equations and 2 unknowns. So what do I have? The first equation, the one in blue, let's use blue, says that 8x is equal to ax plus bx. If I cancel x everywhere, I get the equation that a plus b is equal to 8. The second equation, which is orange equation, says that 1 is equal to negative 3a plus 2b. So, negative 3a plus 2b is equal to 1. Here is my system of 2 equations, 2 unknowns, and you can, whatever method, right? No one cares which method you use. You can guess, you can graph, don't. You can do substitution, you can do elimination, toss some bones and look at the, I don't know, whatever works. I will multiply top equation by 3 and add 2 equations. That will kill off a. So when I multiply 3, I get 3a minus 3a is gone. Then I get the 5b over here. And then 3 times 8 is 24, plus 1 is 25. And I see that B is 5.
Where'd you get that?
Alright, redo that a little bit slower.
Yeah,
A little bit slower. Okay, fine. Multiply top equation by 3
Why?
to cancel A
Oh.
when I add equations. So when I multiply top equation by 3, I get 3A plus 3B
Oh, jeez.
equals to 24. Say, not here. And as I mentioned before, not coming either. I can prove it to you. Why not? When you add two equations, that's a 5b equals 25, and b is 5. And from the first equation, if b is 5, a must be 3, right? Because you have a plus 5 equals to 8, a is 3. So now you bring these 3 and 5 back to the top over there. So a is 3 over x plus 2 plus 5 over x minus 3. And that's the answer we were looking for. Welcome to partial fraction decomposition. There was no calculus, there was just algebra.
Yeah, and then you have to integrate, right?
Oh, that's later. We're not doing calculus yet.
Oh, okay.
Because we need to see the procedure, then we need to learn the 4 cases, we need to learn to set them up, and then we can do some calculus.
Oh, glad I'm not taking it.
Why are you glad?
Hmm?
It's fun.
So you're always
I mean, it's
adding
fun if you don't have to do the work. Then it's fun.
Okay.
How does that pooling work that you showed us there?
What pooling?
Where you pull the A's, not or the X's, and then
No, I don't know.
Well, I circled all of the terms that are x's, right? And that's the blue equation. And then I circled all of the terms, well, not circle, underlined all of the orange ones, and that's the orange equation. And you cancel x everywhere. Now, when we get more complicated cases, you'll have also x squares. You pull them for the equation, you pull x's for the equation, then you have 3 equations, 3 unknowns. If you have x cubed, now you have 4 equations, 4 unknowns. So the amount of these will tell you how many variables. Yes?
Oh, so before when you multiply the 3 across, couldn't you have just like isolated one of the variables?
That's called substitution method, and I said yes, whatever makes you happy.
Okay.
Your happiness is our primary concern.
Alright.
Like United Airlines, right?
oh, so for that, why do you put substitute instead of the
You can use substitution, you can guess and check, right? Sometimes it works, right? When you have a plus b, like what can you have as integers? Well, it's not always integers, you will get many times fractions, but 1 plus 7, it doesn't work. 2 plus 6, it doesn't work, right? 3 plus 5, oh, that worked, way, right? You guessed it. But there are no guarantees that the two numbers that you are guessing are integers. They could be fractions. So good luck guessing 21 over 5 plus 17 over 5. You know what I mean? So because that could also easily be the answer, and many of the answers would be. So whatever way you know, and your favorite way to deal with the pre-calculus system, do it, okay? No restrictions. The goal is to get through the algebra so that we can integrate into lns and inverse tangents and these things that we, I don't know why, but need. This technology to solve this. You know how long Wolfram takes to solve this? Exactly, 0.3 of a second. Very good. I don't know either.
Because
to figure it out.
the reasoning is because education is not caught up with technology.
I think
There's
that's
too
true.
much money in education.
Yeah.
It's called business.
Pretty much.
It's business. All right, so this Calculus2 incorporated. Let's go. Now we are going to. I want to present all four.
No, I'm just throwing some out. Did you miss me?
That was that was efficient. I don't know if it was efficient.
He throws the stuff away and doesn't leave it, on the floor or something.
That is, yeah. Okay. All right. Hi, everyone. Here are the four cases. This is the stuff you are memorizing. This is 4 cases for setup. Memorize them, yes. So cool. Love it. Yeah, sometimes I don't know what is that. Sounds like share. Same. All right. Have you ever listened to a share song? It sounded the same.
I did.
Yeah.
I like it.
I'm not changing.
I have gay friends, so I mean, come on.
Oh, it's getting spicy now. I love it. Let's push it more. All right.
You don't know what share is? I was about to say, her ex-husband ran into a tree. How are you going to run into a tree skiing? You didn't see that thing?
First case is the linear case, the one that we actually had. When you have something, and I call that something blah, divided by x plus or minus c. Why do I say blah? Because you see over here, we have 8x plus 1. We could just have 5. We could have anything. It doesn't matter what's in the numerator. The 4 cases all depend on what's in denominator, which factors you have in denominator. So the blah over x plus or minus c is actually, this was the example of it. So that's what that's why I write blah up there. And the setup for it is a over x plus minus c, which is exactly what we had in our setup. If I go back now to my problem over here, observe what I had as a setup. I had a linear term, and I have a over the linear term. I have another linear term over here, and I have now b over that linear term because a was already taken. Can you have 10 of these? Yes. Now you will have 10 variables. You will have 10 equations with 10 variables, and then by Thursday next year you'll have it. If you do it right. The next one is the repeated linear. So here is the blah. Again, we don't care what's in the numerator. We care that the denominator was squared. The setup for that one is going to be a divided by x plus minus c squared plus b divided by x plus minus c. So this is the setup. The next one is the unfactorable quadratic. So you have ax squared plus bx plus c. It's prime. You cannot factor it any further. So let's say you have x squared minus 16x plus 1. You cannot factor this. This is prime. X squared plus 1. That's prime. You can't factor it. Yes, you can factor 2 complex numbers, but this is not involving complex realm at all. So you have an unfactorable quadratic. It's prime, and the setup for that is ax plus b divided by that prime trinomial. And finally, the last one, right, 4 cases, is the repeated quadratic, which is prime, and that one is going to have ax plus b divided by ax squared plus bx plus c, everything squared, plus cx plus d divided by ax squared plus bx plus c. So these are the 4 cases for setup. I haven't showed exactly all of them how they used, but for now, I just want to point out a few of the patterns that you might not notice, which will help you deal with memorizing these. So the first thing that we see is that if the exponent is 1, if you have a linear term, you have constant up there. And if it's squared, you have a linear up there. Do you see that it's always a 1 exponent less? The next one is, observe that these are just copied on denominator, right? And when it's repeated, it has 2 parts. And you see that it's repeated with the square and then without the square, repeated with the square and without the square. So there's a lot of symmetry in these that you can exploit to memorize these 4 cases to set up things. The amount of A, B, C's, and so on you have is eventually going to be the amount of equations and variables that you have to solve for. So you are hoping not to go past C, because C is already 3 by 3 case. And 3 by 3 case takes time to solve. On your exam, you are going to have a problem where you are just going to set up this. It might have 5, 6, 7, 8 variables. You are just doing the setup, and that problem should take you no longer than 1 or 2 minutes. And I'm going to teach setup right now. The second problem from this section on the exam 2 is going to be the calculation with partial fraction decomposition. You come up with A and you come up with the B, and then you integrate, right? You're doing the integral. So 2 problems on the exam from this section, and one of them is technically a gift, and the other one is probably going to be the longest calculation on the entire exam, therefore it should be done last, right? You don't want to get stuck on that as a first problem and waste 45 minutes, you know, grinding through and trying to fix it. So whenever the partial fraction decomposition is, that should be your last problem, because the calculations for this thing is just way too long and annoying, but such is life. It's a good effort right there. All right. So here is we are learning the setup. So blah over x minus 3, x squared plus 4. I am learning the setup. What do I have? Well, the first one is linear, second one is linear, and the third one is prime. For linear, I have A over linear, plus next one is linear, B over that linear, which is x minus 3, and the third one plus, that's x squared plus 4. That is this. Now A and B are both used up, so Cx plus D. Are we all bueno on this? I have 1, 2, 3 factors in denominator. I have 1, 2, 3 fractions over there. Number of fractions has to match the number of factors in your denominator.
Why wouldn't you combine?
Oh, we will. That's the part of calculation. We are learning how to use the formulas to just make the setup. This is the 8-step problem. The first part is you see the integral and you curse. That's the first step. Second step is to set it up with a partial fraction decomposition. Third step is to come up with those equations and get A, B, and C. Then you bring that back into the integral, give each one separate integral. Then you have your U subs and the rest. Out of fun, I created a problem when I was a tutor for one of my students to practice. I created a problem where you start with partial fraction decomposition, and all of the things that you get at the end, each one of the individual ones that you get, one had to be solved with U sub, one had to be solved with by parts, one had to be solved by trig sub. So I created one problem that covered the entire chapter.
You're not going to do that on the test, right?
You should give us one like that just for the exam. We have one problem.
Don't listen to Olga.
That's the mantra for tonight, right?
I do kind of want to see the problem.
Hmm?
Yeah, I kind of want to see it.
I created that problem for student to practice, right? No, I can't find it, but I can make it up. You can make it up too.
No, you don't get that.
All right.
My kind of problem.
But that's next step. Combining denominators is the next step. You see, over here, I have a problem. I did the setup, and then I combine denominators, right? But what I have over there is just this part, just that, because I need to make sure that you guys know what to use in that mess. All right, let's go next one. Blah over, this is next example. We are just practicing setup. Blah over what? Let's go with x minus 2 times x plus x squared plus 3 squared. Whatever. Done. What's the first one over here? First case, linear, so a over x minus 2. Great. How about this one? It's the last one, fourth case, yes. So you are going to write 2 of these, right? Excellent. So as long as you are getting out to set this up, the rest of the problem is a grind in algebra, which is probably what scares you more than initial case. So now a is taken, so this is going to be bx plus c, and now a, b, c are taken, so dx plus e. This has 5 variables, therefore system that you get would be 5 by 5, and it will take very long time, because 5 by 5 system is reduced to 4 by 4, and then 4 by 4 into 3 by 3, and 3 by 3 into 2 by 2, and then you have to bring all of the variables back. So it would take an hour or so to do it by hand, which is why we have a Wolfman, right? Is it Wolfman? Is that how you call it? Wolfman?
So what do you call that for?
Bx plus c, yeah, and then dx plus c.
Yeah, that's what we do.
Because it's a quadratic over here. All of your quadratics, this is a quadratic, this is a quadratic, they have linears on top. Linears have, okay? So that's the pattern that you have to memorize. Otherwise, do. Good. Well, now that you are so well versed with these things, it is time for us to do some integration.
Which cases did you use on that last?
1 and 4.
1 and 4.
Fell through the wall, you mean?
Well, that would have been even funnier.
Zero concern for human well-being. I love this class.
I told you to stop on it.
All right. Let's integrate. Let's see some of the fun stuff over here. Say we are looking at the problem 39, and we have 81 over x cubed minus 9x squared dx. Oh, by the way, did I notice that? Did I tell you that you will be using factoring as well? You see, that denominator is not factored.
Really?
Yeah.
So what are the factors over here? So we factor out x squared, and what's left? X minus 9. Dx. Good. What are the cases that we have?
You have a linear and you have a number of two.
Yes. Numbers 1 and 2. Very good. Number 2 first and then number 1. Whatever. So we have... So we are going to do partial fraction decomposition. So we are only focusing on 81 over x squared times x minus 9. So this is going to be a over x minus 9 plus b over x squared plus c over x. X squared is the repeated linear. You can think of x as x minus or plus 0. And then a square on it, right? That would fit this case over here. If your c is 0, it would fit x squared fits that case. So our setup is this one. And now we go and we use algebra. Now when I teach elementary and intermediate algebra, this is exactly the type of question they would have to add these fractions. Now, the way I explain this in algebra is I say, let's play the game of what's missing. Because you already know what the common denominator is, so you just play the game of what's missing and multiply into each one of these. Yes?
Which steps did you use again? You
1 and
said
2.
it was 2.
1 and 2.
1 and 2.
First one is 2, the second one is 1. So what is missing on my first one? X squared is missing. What is missing on my second one? X minus 9 is missing. And what's missing on the third one? X minus 9 and x minus 9. So this is what it's missing in order for me to have a common denominator. So now 81 over x squared times x minus 9 is equal to x squared x minus 9. So I have ax squared plus bx minus 9b plus cx squared minus 9cx or whatever, 9cx. Because this x times x and then x times negative 9, so that multiplies into c, so you have cx squared and negative 9cx. Denominators drop because they are the same on both sides, and we only get to compare the top, right? Now, I'm going to write this out. You don't have to do this, but I'm going to write it out so you guys can see it. I have 0x squared plus 0x plus 81 on the left-hand side. On the right-hand side, I have ax squared plus cx squared plus bx minus 9cx minus 9b. I hope you noticed that I grouped my terms in a descending order of powers, and I added zeros for whatever it's missing because I need the squares and linears and constants on both sides so I can equate them. So I picked up the term that has x squared, and I pick up the term and x squared, and I list them first because x squares are listed first. Then I have listed the single x terms, linear terms, and this one has no x, that's a constant term. So now I use colors, 3 colors for 3 equations. Color number 1, let's say red, is going to be for my x squares. You know what? Drop x squares right away. You don't need them. You need a plus c is 0. Because who cares? X squares, bye, right? The next equation is going to be blue. That's these ones with x's. Drop all x's. You have b minus 9c equals to 0. And finally, the orange equation at the end is negative 9b equals 81. That's the orange equation. What are your questions? So do we all get the colors? We know that the expression is coming from getting the common denominator. We are comparing the numerators only because denominators are the same, so get rid of them. This one was only constant. I see x squares, so I put in placeholders for x squared, x, and then I have 81. And now put everything in descending order on this side. So x squares go with x squared, those are all my reds. Then blues are all the linears. And finally this one. You already see that the orange equation is going to give you that b is equal to what? Negative 9, plug it in here, c is equal to what? And then plug your c here to get your a. Right, some of these equations are going to work this easy, which is nice. So to solve this from here, we calculate that b is equal to negative 9. Then we plug that in. And we get negative 9 minus 9c is equal to 0. So c is equal to negative 1. Thank you. And then you take that and you plug in there. And you have a minus 1 is equal to 0. A is 1. Ha! A1. I know, right? Why is that horrible? It ruins it. Now we have our A, B, and C, and we need to plug them where they belong. And we can finally start doing the calculus, right? We can start integrating.
Are you going to give us 2 extra pages on the exam just for work? Yes. I'm already at 1 full page.
Yeah, that's what. So you start, and then you flip, and then on the back of the page you finish it. Right? Remember that every other page is blank. So then you move to the next. I know. Hold on. How about sine to the 6 times cosine to the 8? I give you a booklet of 30 pages. Right. All joking aside, right? So now we have our integral of a is 1 So what is my a? 1 over x minus 9. B is negative 9, so minus 9 over what? X squared. And then C is negative 1, so minus 1 over x dx. Great, we're done. We'll just integrate each one of these. The first one is the u sub, and you will get ln answer for it. You will memorize this, but believe me, you will be skipping u sub on this one. Right? This will be automatic response. Let's spell everything out. So integral of dx over x minus 9 minus the integral, you can kick 9 out, x minus 2 dx, minus the integral of 1 over x, that's the basic integral, right? Yeah, it's ln x, good. So now the first one is ln of x minus 9. Now the next one is going to be plus. This is minus 1, so it will be 9 over x, right? And the last one is minus ln of x in absolute values plus c.
Now you couldn't have come back in a roll without doing all that.
Nope. That's the beauty of the method. It's for this.
This is why they say calculus.
This is algebra.
This was algebra, yeah, exactly. Your calculus was to integrate Calc 1 things.
Let's just say, for example, we forgot to put the absolute value.
Ooh.
Minus half point.
Okay, forget that.
Absolute values are important. Then you do this, you get a definite integral, then you get to calculate the values as well. There's a lot of cool stuff. So what else should we do? Give me the number from 27 to 64. (27 to 64), let's go.
52. Anybody else speak for that?
Yeah, somebody else pick up.
Yeah, somebody else pick it. I don't want to pick it.
36.
52 was said
Okay.
twice. 36.
I don't care. I'm tired. I want to go to sleep.
He doesn't speak now.
36 will definitely not put you to sleep. Let me tell you that. 52 is less writing for now. So let's see.
That sounds good.
Integral of x squared plus 3x plus 2 divided by. Oh, they're so nice. They factored out x for us, so we don't have to worry about it. X squared plus 2x plus 2. There's a dx at the end. Forget dx. It's not there for decoration, right? What now? Excellent. Cases 1 and 3. Very good. Cases 1 and 3. First one is linear. Second one is prime quadratic. So very good. 1 and 3. So we have this we have x squared plus 3x plus 2 divided by x squared plus 2x plus 2. And in the setup over here, I have the linear first, so that's a over x plus, and we have bx plus c divided by x squared plus 2x plus 2. Now we multiply by what's missing. The first one is missing the entire x squared plus 2x plus 2. And the second one is just missing an x. So we have x squared plus 3x plus 2 divided by x squared plus 2x plus 2 equals 2. Common denominator is x squared plus 2x plus 2. And in the numerator I have ax squared plus 2ax plus 2a plus bx squared plus cx. Denominators drop, and I go with the red for the square equation. So a plus b is 1, coefficient of x squared. Blue equation are the ones with x's. I have 2a plus c equals to 3. And finally, orange equation, and that's the one that saves the day. 2a equals to 2. From that equation, we get that a is 1. And then you bring a to both of these equations here. The first one gets if a is 1, b is 0. And the second equation, if a is 1, c is 3. So I have the integral. Do we have limits? No. Integral, open parenthesis, a is 1. So I have 1 over x plus, the second one is bx plus c, so there's no b, it's just the 3 on top. And we have as a denominator x squared plus 2x plus 3 dx. Nice. Well, the first one is
Plus 2.
plus 2.
Plus 2 and plus 2.
Thank you. Okay. Who picked 52? So, what is the first integral? ln absolute value x. Thank you very much. So, yes, excellent. What are we going to do for the second? What are we going to do for the second integral over there? As I walked. Huh? Ah, we can't. There are no factors. There are no factors, so we can't decompose it. Yeah, I lost the door. Don't worry about it. We'll say. We'll go. I said we'll go at 1 o'clock. Oh, I thought it was 0. No, b was 0. Ah, I plugged in wrong value. Yes. So c is 1. Yes, c is 1. Fix that. Great.
I'm still right. He's on B here, right?
Yeah, b is 0 because a is 1, so b is 0, and then a is 1. That's 2. 3 minus 2 is very good. Very good. Thank you. I mean, that changed the constant from 3 to 1. How do we integrate this? It's my fault.
We split them all up.
Yeah, you can do 1
Each
over
fraction,
x
1 over
squared,
x squared, 1 over 2x.
No.
Okay, then I guess you don't do that.
We can't split when it's in denominator. We can only split if it's numerator, not denominator.
Okay.
Oh, that's right.
Thank you. So if I complete the square, what do I get?
X plus 1.
Yeah, but what do I get to do for integration if I complete the square?
Store over? I don't know.
A trig sum.
Trig sum, exactly. So the first integral is the basic ln. The second integral over here is the trig substitution integral. You have to complete the square, and then you use. So you get x plus x plus 1 squared plus 1, and then you do the triangle and you do the entire problem from 8-4 on this part only. This is why I said we can create a problem where these parts over here, one is ln, one is trig sub, one is by parts, right? Because u sub, they can all be anything else. Just like, remember the tangent line problem for Calc 1? The tangent line problem for Calc 1, you had to take the derivative to find the slope, right? Now, the method you're going to use depends on what function you have. The method for tangent line works for entire chapter 3, or whatever is the chapter. And then you say, oh, this product rule, oh, chain rule, oh, right? So every single... So now, within partial fraction decomposition, when you get these things at the end, well, it's a toss, right? On which one? So now we get to review trig sub. Do what? Make sense? All right. All right, so it's time to do partial fraction decomposition. Over here we have x squared plus 2x plus 2. X squared plus 2x plus 1 plus 1. X plus 1 squared plus 1. That was my partial fraction, that was my completing the square. So now I have two integrals to worry about. Integral of 1 over x dx plus integral of 1 over, and now I have x plus 1 squared plus 1 dx. The first integral is ln absolute x plus, and the second integral using our triangle over here, theta. We have two legs, so this is my x plus 1, and this is 1, and this is a square root of x plus 1 squared plus 1. So when I do this, I get that my tangent theta is equal to x plus 1 over 1. It's just x plus 1. So x is equal to tangent theta minus 1, and the dx is equal to secant squared theta d theta. And the blue one is cosine of theta is equal to what? Is 1 over the square root. So the square root is equal to secant, right? Theta. And then I need to square it because I don't have the root on this side, so square it. There we go. And this is x plus 1 squared plus 1. So now I have the integral of dx on top is secant squared theta d theta divided by secant. Oh, look at that. Come on, you couldn't have better. Integral of d theta. Oops, I didn't hit shift. There we go. And this is now going to be ln absolute x plus theta plus c, and you convert back using the inverse tangent. So ln absolute x plus inverse tangent of x plus 1 over, why put that over 1? It's just x plus 1, yeah. X plus 1 plus c. Look at that. Not even a page, right? 2.5 pages for you. So this one was juicy. I like it. So have some creativity in life when someone says, what do you know? Or take your time for the Thanksgiving dinner to explain this problem to everyone.
You know, what if they ask you, like, all right, how do you apply it in the real world? Then I'm gonna feel stupid because I'm like, oh, I don't know what
That
would be
would be
$10.
That's what it is.
I make more than that.
How does this
So, what's the next one?
How does this work?
It's coming up. The winter is coming.
Isn't it spring?
You're donating for each one of those. You know that,
What was
right?
that?
Yeah.
Don't you
Hey.
want to what?
Yeah. All right.
What?
So, next. We have plenty of time. Pick a number.
$38.
38. Nice one. It's a definite integral, so you get to compute the limits now.
Oh.
Harm, you gotta stop letting that second.
That's- But no, it's nice. It's nice. Look at this.
Oh, he says it's nice.
Probably has a
Yeah,
door
never mind.
All you need to do is to factor, and you can almost do it in your head.
So if you have something like this on the exam, and we do all that like A, B, C stuff, and figure out what A, B, and C is, and then we plug it in, but we don't integrate it, how many points would you get? Like half?
Yeah, I don't know. Like half of a 20-point question.
So this would be like 20 points?
It was like 3 pages.
Yeah, okay.
We want to do it for
So like 10
4.
points then? So 20?
Actually, I wouldn't mind it for like 2 points. I mean, if it wasn't for this two form would exist, so the most modern technology. So.
Still, you sat down and thought of this.
Thanks for this stuff.
Long remaining and got 3 W's. Thanks. Okay. And 1702.
Just past that.
Good. Yeah.
That's everything.
So what are the factors that we get here? X minus 8, x plus 4, and this would be 2 case 1s. Very good. 2 case 1s, so this one just flies. Quickly you get a 2 by 2 at the end. So we have A over x minus 8 plus B over x plus 4, which gives us AX plus A4 or 4A plus BX minus 8B divided by x minus 8 x plus 4 so AX plus BX plus 4A minus 8B is equal to 0x plus 2 as a placeholder. So I have my red equation, which is A plus B equal to 0, and I have my blue equation, 4A minus 8B is equal to 2. So when you are looking at these equations, notice that the equation on the bottom can be divided by 2 to reduce numbers, and that would bring our A to be 2A. So if I multiply the top by negative 2, we will have negative 2A minus 2B is equal to 0, and then I'll have 2A minus 4B equals to 1. When I add, these guys over here would add to negative 6B, which is equal to 1, from where B is equal to negative 1 over 6. And if B is negative 1 over 6, A must be 1 over 6 because they're opposites. Right? They're opposites because they add to 0. Additive inverse. So now I have A, that's 1 over 6. So integral 1 over 6 over x minus 8 minus 1 over 6 over x plus 4 dx, which equals 1 over 6 ln absolute x minus 8 minus 1 over 6 ln absolute x plus 4 plus c. Now, that's already the answer, but we can flex, right? We can factor out 1 over 6 and then combine logs using the log rules. So that's the boss move. So it becomes this, right? It's not necessary, but it's so damn cool. Bueno. Oh, we have limits. Not plus C. Not plus C. We have limits 0 and 5. 0 and 5. 0 and 5. It's 1 over 6 ln, and we plug in 5. That's going to be negative 3 over 9 minus plug in 0 ln of negative 8 over 4. So now this is 1 over 6 ln of 1/3 minus ln of 2. Absolute value kills the negative. And now we combine this. So this is 1 over 6 ln of 1 over 6, right? Because it will be 1/3 divided by 2. Half of 1/3 is 1 over 6. Okay, I like it. If you want decimals, just go punch this in the calculator. 0.00 number. Cool, right? Well, a part of the homework is going to take 10 hours for 3 questions. To plug in the MyMathLab, the minus sign is off, or the form doesn't match the same right thing that they have. Yes.
I mean, not math, like math, my math, whatever. My math, that's it.
In this case?
In any case.
Yes.
They let you do with
So next week, the title of the lecture is improper intervals. Improper intervals are going to have type 1 and type 2. Type 2 will be concerned with what you have. We are going to integrate 1 over x from 0 to 7, in which case you have that issue, that one side. So we are going to have type 2 will have the vertical asymptote, and we'll see that's the bad case. And we'll also learn that even though in some cases when area under the curve is leaking, meaning, you know how e to the x doesn't really, like e to the negative x doesn't really touch x-axis ever, but it will actually have finite area underneath, which is why the bell-shaped curve, right, which is leaking on both sides, still has the probability under it to be 1. So it's normalized to have a probability of 1, but your interval is from negative infinity to positive infinity, which is the difference of the statistics that we teach, which is why it's not transferable to many schools. Our statistics is introductory statistics. The real statistics is Calculus2 based, so that you can, when you have the bell-shaped curve, you can actually integrate for z-scores and other things. You can do integration. In our case, you get the chart, and you have to look up z-scores and these things. So that's the difference. So, cool. Well, we can do one more, right? There's energy. Energy is high, all-time high, right? You don't look too well.
No, I'm looking up this geometry. He was asking like he did this.
Better?
What's this?
Good. Yes. Oh, I multiplied. I think it's 2. I multiplied with negative. Yeah, I fixed both equations at the same time. All right, let's do one more because we can, and then disappear into the night.
Is the next one is 8.6, or is it?
No, one more problem from this.
No, I mean the next section.
Oh, the next section is 8.6, I think. Yes.
How many sections are in chapter 3?
I will tell you.
Do we have a syllabus to let us know?
No, we don't.
Yes, we do, but it's not in your hands. Integration strategies, other methods of integration, numerical improper. So all the way to 8.9. And yeah, there is an extra section. And then they took off the differential equations. There was one section and pushed that into its own chapter. And its own chapter for differential equation has 9 sections, but we will only pick and choose certain things. So chapter 9 is going to be a single lecture with the highlights, because you are going to have the entire course on differential equations if you need differential equations, and so there's no need for a chapter here. All right, let's do one more problem.
Chapter is basically like a topic somehow.
Oh, you haven't seen 10 yet. Just relax.
That was 10 words.
By all means, by accounts and students. Just think like you're at the dentist, right? It's gonna be better tomorrow when it's over.
I think that all the time, yeah. I do. I'm like, I can't wait till May.
So right now is the B part with the pss, 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 right? That's currently.
I need to pass this class to graduate.
Me too.
This is pressure on you.
Pressure on.
Yes.
Pressure on me for you to pass the class.
Yes. I'm gonna pay to fill out the graduation application, so I gotta pass.
Oh no, it stays on the file. It's okay. You don't have to refill it. So.
What are the numbers that we're picking from again?
We didn't do anything in 40s, right? We did in 30s and 50s. Give me something in 40s. 45? Why not? X minus 5, and then x squared x plus 1 dx. So no pressure, you have 18 seconds. Go.
Something to that. I just read it, that's good, okay?
I messed this completely up.
Because it has to be something.
I just started to go down.
I don't know what the fuck to do.
Which cases are we using? 1 and 2, very good. Well, 2 first and then 1, yes. But yes, 1 and 2, good.
What do you do with the x squared? Because I know it's x squared.
This is x plus 1.
No, the x plus 1 is my b. That's my lower. My other one. Oh, I know. Should have put this. It's ax squared plus b over x. Okay. Then I'm going to have because remember, it's an x squared, right? So on the second part of it, it's just 1. So it's the first one. No. If you have a being x squared, then I'm believing that a is going to be over x. I mean, b is going to be over x. Because if we look at this here, because whatever it is squared, right? Then affects whatever it is squared, then whatever it is single. So I think it's that. So we think too. And then you see, then you have plus c plus 1. I mean, plus c in the denominator of x plus 1. And now we got the other.
The A, B, C, yeah.
I got the C and I have the A.
I have the a is the a over x squared.
Yeah.
I just want to make sure I'm going about this correctly.
Oh, no, I feel about
X plus 1, x squared. Yep, that's it. And then you do this.
Now the denominator is always the same as that, correct?
When you add them, when you multiply through. So yeah. Good. I'm gonna do this and then.
So wait a second, if you multiply these. Wait, what denominator is coming
Wait,
from
why?
that, right?
You already have x. You can't do x squared. You just do 1x. Only 1x because you already have an x. You see the x in the denominator? So what's missing?
Oh,
It's
just
missing
another x. Yeah.
X. So that's why there's no cube. I'm gonna do it. So let's see. X minus 5, x squared, x plus 1, and we have a over x plus 1 plus b over x squared plus c over x. This is why I write it on top and the bottom, so it's not. I go x squared,
No, wait, where's your
x
denominator
plus
coming
1,
from?
x plus
It's
1,
the same, right?
x plus 1. Yeah, the denominator must be the same on both when you multiply each term. So we can disregard the denominator. It's going to be x minus 5 equals to ax squared plus bx plus b plus x squared plus something explodes probably.
No. I have a over x squared plus b over x plus c x plus 1. It doesn't matter. Right?
Oh, it doesn't matter which order.
Okay.
But you just have to. Okay, so you can put these a, b, c anywhere, right? Because they can be in any order. It's all commutative. You just have to be very careful when you're plugging things back in that a goes for a and b goes for b, because what universally has to happen if x squared gets a 3 on top, some people had a there, some people had b there, right? We all have to get 3 above x squared. Okay? That's something that has to happen. So I have negative 6 over x plus 1. Do we have that? And b is negative 5 over x squared. And then 6 over x. I hope. So, integration. Anytime when you see a constant over a linear, it's always going to be ln. And you will always get the same thing with if you do u sub, the coefficient, the constant thing or number on top goes in front. So you see your negative 6 over here, and you see your 6 right there. It's a pattern. It's always the same. And then when you have 5 over x squared, y was a negative, this is a negative 2, it becomes negative 1, so it becomes a positive, so 5 over x. And then I combined these guys together as ln x minus 1, so x on top and x minus x plus 1 on the bottom, as I combine them using the log rules. We don't have calculation here, so we just leave it right there. And that's it. Partial fraction decomposition. What's better, this or trig sub?
This is better.
This is better than trig sub?
Yeah.
All right.
Can you actually